Okay, let's go ahead and get started again. So we're looking at our spectroscopy lab, and so depending on where you're looking, it's either lab 13 or lab X. So what I'm going to do is go through the lab as we would have done it in class, but I'm going to show you what parts we're actually going to do. So this lab actually takes a big group effort normally. So normally we would work in groups of 6. And what you're seeing right now is the top of sort of my recommended workflow for this lab. So normally what I recommend is working in groups of 6, but you split up into 3 groups of 2, where the first 2 people are going to work on dilutions. The second 2 people would work on calculating molarity. Third 2 people would work on colors, and the colors from part D. And then once the first set of dilutions are done, you would have 2 people continuing on to make part A, test tubes 1 through 4. Then you would have some people moving on to part B, where they'd find the absorbance of test tube 5 at different wavelengths. And the people who made the test tubes 1 through 4 could then move on to finding the absorbance of those at their maximum wavelength. And then we're going to have 2 graphs. So this is the whole lab here. So it's got a lot of stuff. However, you're only going to be doing the stuff that I have highlighted here. The other stuff would be the lab stuff, which is fun to do, but it's also kind of a hectic lab trying to organize everything with a group of 6. So I would say if you talk to people who've done this lab last semester, they probably would say you're very, very lucky to not need to actually go through it. But what I want to do first is take a look at calculating out our dilutions. And where I'm going first is 4A. So 4A will be the first calculation you're going to need to do, and it is an M1V1 equals M2V2 dilution. So you're going to calculate the volume of the concentrated cobalt chloride solution that you will need to make 500 milliliters. So your M1 will be the molarity of the bottle we would have given you. So on that little push cart that we have right by the door that leads to the stockroom, you would have had a dark solution. It's a very dark purple, kind of a purplish blue, and it would be labeled 1.50 molar. So that's the solution we would have given you. And what your goal is to make a 0.15 molar solution. And you need 50 milliliters of that solution. So what you're calculating here in 4A is what your V1 is. So how much of our solution do you need to make your stock solution? And so you would make your 50 milliliters of your stock solution, and from that you would then make new solutions. But the very first thing you're going to do again is make that stock solution. So this is the first calculation that you will need to do for that dilution, right up here. So this is coming from 4A in part A. All right, so I want to show you a couple videos that will take you through how you would do this. For those of you watching this video online, I apologize, there'll be a little jump here.
The first thing we're going to talk about today is how to use a pipette to dispense a precise volume. This is actually a 10 ml pipette. It'll be printed somewhere on it. To use a pipette, you don't suck with your mouth like a straw. You use a pipette bulb. They may be blue, they may be red. These are equivalent. Inside the neck of the pipette bulb is a cone of squashy rubber. That's what actually forms the seal. So when you want the seal, you push up with your pipette holding hand and you get a decent seal here. I'm going to be dispensing this green liquid into this empty container, 10 mils of it. The first thing to do is to actually wash the pipette with whatever this liquid is, because who knows what's in there right now. Flatten the pipette bulb and apply suction to get some liquid inside. That's all you need to do. Now invert this, and by releasing the pressure on the top, I can let the liquid all the way up above the calibration mark, rotate the pipette so that everything gets wet with the liquid, and then dispense it. And I can squeeze that out into a waste container. It's a good idea to have a beaker just to put waste in, rather than trotting back and forth to the sink all the time. We're now ready to dispense 10 mils into this flask. Flatten the pipette again, and this time apply suction until the liquid in the pipette is above the calibration mark. It will move a lot faster when it's in the neck rather than in the bulb. Once it's well above that line, remove the bulb and capture it with your index finger. Use your index finger, not your thumb. And the calibration is actually a line, a circle around the neck of the bulb. Hold it so that it is level with your eye, so that you are seeing a line and not a ring. And by releasing pressure with your finger, you get the top of the meniscus down to the line. That's now ready to go. If there's a drip on the tip, touch it to the dispensing vessel, place it over the receiving vessel, and allow to flow out. Do not squeeze it out at this point. You need to be patient and let gravity do its thing. This is now dispensing 10.00 mils, or an aliquot of 10 mils. And once the flow has stopped, you count 10. 1 hippopotamus, 2 hippopotamus, 3 steamboat, 4 steamboat, 5 Mississauga, 6 Mississauga, however you wish to do it. There may well be a drip hanging on the end, so you touch the tip of the pipette to the liquid in the receiving vessel to break the surface tension and bring it out. Now you may notice I'm holding it up against my arm for color contrast. There is some liquid still in the tip of the pipette. Do not blow that out. The pipette is calibrated to retain that little driplet of water. In the technique that I've just used, I have now dispensed 10.00 mils. That's exactly 10 mils of, it's actually bromocresol green liquid, into this flask. This is a 100 ml volumetric flask, and we'll show you now how to use volumetric flasks themselves. The first thing you should do is wash it to make sure that you have it clean. If it looks reasonably clean, just a rinse of distilled water is usually enough, again into my waste beaker here. It doesn't have to be dry because you're going to be adding distilled water to it anyway, so the small amount of liquid there is irrelevant. Here I'm going to dispense 10 mils of a liquid into that flask. There we are. Okay. And again, we allow this to dispense directly into the volumetric flask this time. And resist the temptation to use the bulb to speed the process up. Once it has stopped, and you've counted 10, touch the tip of the pipette to release it, and away we go. Now at this point, use your distilled water bottle to wash down the sides, and we'll be adding. Now there is no point in squeezing 100 mils out there. So if you want to be quicker about it, just open the neck of your distilled water bottle and pour in until it's about 2/3 full, like this. Now at this point, take the container and put the cap on. Notice that I'm holding the cap on with my fingers, and invert several times. Let the bubble do the work. You're not playing the maracas here. Just allow the bubble to stir it so that you've now got a uniform solution behind. Take the liquid off and add water until you're almost at the calibration line. Now, the calibration line is actually where my finger is. So we'll get it fairly close fairly quickly. Now that we're almost at the top, instead of using the squeeze bottle, which is not actually all that easy to contain, use a dropper. And I'm going to get my head down so that I'm seeing the line of the volumetric calibration rather than as a circle. And I said, do this at eye level. Head it dropwise until the bottom of the meniscus is tangential to the line. If you want to, you can use a burette reader card to make that a little more obvious. I think I've got about one more drop to go here. There we go, and 2 drops. The meniscus tangential to the calibration line. Now that I've got it actually at the line, again, put the cap on, hold it with my hand, and invert several times to make sure that I've got a uniform solution. And this is now a 100.00 mil solution of 10 mils of my initial liquid.
We need to calculate the molarity, so we need to know what molarity all of your solutions are. And where that's coming from is right over here. So you were told in the initial dilution that you were making a 0.150 molar solution. That will be your M1, and you will be using your M1 V1 equals M2 V2. Now for solutions 1 through 4, this is your V1 here. And I have 1 through 5 highlighted here, but it's really 1 through 4 because your test tube 5 did not get diluted. It's just the 0.150 molar. So you're going to run this calculation again for solutions 1 through 4. And for those, V1 is right over here. M1 is this right here. V2 is going to be the water plus the stock solution. So it's how many milliliters you put in total. And for each one of these, you are putting in 5 milliliters. So for instance, in test tube 0, you put in 5 milliliters of distilled water. For test tube 1, it's 4 plus 1, total of 5. For test tube, I'm going to jump down to 3 here. 3 is 2 plus 3, again it's 5. So the way we've designed this experiment is no matter which test tube you're on here, you always had 5 milliliters. So that is your V2 for every one of these. And then you'll be solving for M2. So let me come up here. And just to reiterate what I said a moment ago, M1 V1 equals M2 V2. And you're going to solve for M2. So M1, this was your 0.150 molar solution. V2 is the milliliters of stock solution. How much of that 0.150 molar you put in there. And V2 for all the test tubes is 5 milliliters. That is the total of the stock solution plus the water. Okay.
And are we doing that for test tubes 1 through 4, right?
Yes, 1 through 4. You don't need to calculate it out for 5 because 5 is just the 0.150 molar solution.
Okay, thank you.
Mm-hmm. And let me just make sure this 5 is visible there. There we go. Okay, I know this page is very busy with lots of stuff here. But any questions on how you're going to calculate out that molarity? All right. All right, so at this point in the experiment, you would have some of your group members making tubes 1 through 4. You'd have some of your group members calculating out the molarity. And then you're going to have to do 2 experiments with our spectrophotometer. And I'm going to show you a video of this. So one of them, you are going to use tubes 1 through 5, and you're going to examine them at 1 wavelength. And, oops, I'm sorry. So 1 through 5, yes, you're going to do it at 1 wavelength. And for the other part, you are going to adjust the wavelength. You're going to take only tube 5 and adjust it at different wavelengths. So while 1 or 2 people in your group are doing this, 2 other people can be right over here, and they can be examining only tube 5, which is the one that didn't need a dilution, and looking at it at different wavelengths. And the purpose of looking at it at different wavelengths is to find out where does it absorb the best. So under what wavelength of light does your sample take in the most light? Oops. Once you know the proper wavelength, where you're going to take in the most light, then you would come down here and use that wavelength, what we're going to call the maximum wavelength, and you're going to examine all 5 test tubes at that best wavelength. So I'm going to show you a video.
The spectrophotometer is an instrument used to measure the effect of a sample on a beam of light. We can learn a lot about a substance by studying the way it interacts with light. Here's how a spectrophotometer works. A lamp provides the source of light. The beam of light strikes the diffraction grating, which works like a prism and separates the light into its component wavelengths. The grating is rotated so that only a specific wavelength of light reaches the exit slit. Then the light interacts with the sample. From this point, the detector measures the transmittance and absorbance of the sample. Transmittance refers to the amount of light that passes completely through the sample and strikes the detector. Absorbance is a measurement of light that is absorbed by the sample. The detector senses the light being transmitted through the sample and converts this information into a digital display. Let's practice by performing a simple experiment. In this exercise, we'll determine the absorbance spectrum of red food coloring. To begin, set the wavelength to 380 nanometers. With the sample chamber empty and the lid closed, set the display to 0% transmittance by using the zero control knob. There are 2 cuvettes. One contains only milli-Q water. This is our blank. Wipe the blank cuvette with a Kim wipe to remove any fingerprints, and place the cuvette into the sample chamber by aligning the guide marks. Adjust the display to 100% transmittance. Remove the cuvette with the blank solution. Now set the display mode to absorbance by pressing the mode control key. The second cuvette contains milli-Q water and red food coloring. This is our sample. The absorbance of the sample is 0.845. Press the mode control key to select transmittance. The transmittance for the sample is 14.2%. Increase the wavelength by 25 nanometers to 405. Wipe the blank cuvette again and place it in the sample chamber. Adjust the transmittance control knob until it displays 100%. Now remove the blank. Wipe the sample cuvette and place it in the sample chamber. The transmittance for the sample at 405 nanometers is 7.4%. The absorbance for the sample is 1.130. Record this in your lab notebook. Increase the wavelength by 25 nanometers to 430. Repeat these steps with the blank and sample, writing each value in your lab notebook. Increase the wavelength by another 25 nanometers to 455 and test the sample again. By repeating these steps up to 680 nanometers, we can plot the absorbance spectrum for red food coloring. Now that we've finished our first practice exercise using the spectrophotometer, you're ready to enter the lab and try it for yourself.
All right, so you would have done something very similar. So whomever in your group chose to do this part right here, they would have taken only test tube 5 and they would have found the absorbance at different wavelengths, just like the person in the video was doing. And at every wavelength, you would have to calibrate. All right, so this is what you would have done. You would have taken test tube 5 and you would have looked at it at 430, 450, 470, 490, 510, 530, 550, 570, 590, and 610 nanometers. So at each wavelength, you would calibrate with water just like the person in the video did. And you would do this all with only test tube 5. So what you're going to find in the lab notes section now is going to be a data table. And here is your data for this. So what you're going to see here is you're going to see that the numbers steadily increase, and it looks like they're increasing until right about that 0.774, and then they start to decrease again. So two things that you're going to do with this data. One is that you're going to do a graph very similar to what they did in the video. You're going to actually make two graphs today, so I'm going to show you both graphs at the same time. It's a little less jumping back and forth in the video for me. And the other thing you're going to do with this is you need to identify what we call your lambda max. That is the wavelength where you have the maximum absorbance. And in this data set, it looks like it's just about 510. So that is where we're getting the strong, there goes my pen. All right, that's where we're getting the strongest absorption. So that is the highest absorbance number, and therefore it is absorbing the best. The reason we want to know where does it absorb the best is because we're going to run a second experiment, and if we were to choose, say, instead of 510, we chose 430, we're not going to get very good results. We're not absorbing very well in test tube 5, which is your strongest. It's going to be the one with the highest molarity. So when you get to a test tube 1, which has much lower molarity, you might not see any absorbance at 430 nanometers. So that's why we want to choose the one that has the best absorbance, so that when we get to our test tubes that have very low concentration, we can still see an absorbance. So any questions about that idea of choosing the wavelength where we're going to get the maximum absorbance? Okay, so let me show you where you're going to be writing that, and that is for part C right here. Based on part A, what is your wavelength of maximum absorbance? Based on what I showed you a minute ago, you can probably already fill that one in, or you can wait till later. So for this data set, I do want you to write everything into your own pages. So don't just print out the sample data, actually write this into your own. If you don't have the lab, you can write it on another piece of paper. But questions about anything here so far, or about choosing that wavelength of maximum absorbance? All right. And let me just make sure we are recording. Yes, okay. All right, so going all the way up here, we just talked about this experiment right here, where you would have used test tube 5, and you would have found the absorbance at different wavelengths. In just a little bit, we'll talk about how you're going to make the graph. But next up, what I want to talk about is this one right here. So at this point, we're hoping whomever was doing this part right here, making test tubes 1 through 4, is done. And then what we're going to do is we're going to find the absorbance of test tubes 1 through 5 at just one wavelength. And again, that's the wavelength you chose based on the data we just looked at. So at that wavelength, you're going to calibrate only once, and then you're going to put in test tubes 1 through 5 plus your unknown. And that would be for this part right here. So this is part C. So I have a note here not to forget to record the unknown, because a lot of times in class people do test tubes 1 through 5 and they forget to do the unknown. So you're going to calibrate it one time only, record the wavelength that corresponds to the largest absorbance that you found in part B, and then all of these are going into the machine at that wavelength. So in the video you saw the individual there using what we call a cuvette. It looks shockingly like a test tube, but it is not. So in class I would have handed each of you about 4 or 5 of those cuvettes. Again, they look a lot like a test tube, but they are very smooth, and the reason they're smooth on the outside is to prevent the light from bouncing off any scratches. So I would have told you that we never put a test tube cleaning brush in there, and we never even use any paper towels. So instead we use something called the Kim wipe, which they didn't talk about, but they showed you in the video. It looks like a tissue, but it's an extra smooth tissue. Although I have in the past tried using it as a tissue. It doesn't feel very good to me, but works very well on our cuvettes. Works much better than a regular tissue, doesn't leave any lint behind. So that's what those cuvettes are used for. And I think in the video they showed you how to line those up into the machine. So you would have done that again for test tubes 1 through 5 plus your unknown. And here is some sample data. So here's the absorbance at your wavelength of maximum absorbance. You got test tubes 1 through 5 plus you have your unknown value. So from here you're going to do another graph, and you're going to use the graph to determine the molarity of the unknown. But before you can do your graph, you've got to determine the molarities of test tubes 1 through 4, and that's what we talked about earlier. And this is why it's important in the lab, if you were doing this, to have a lot of people and everybody's kind of doing their own part here. So somebody was working on finding the absorbance of those test tubes, but somebody else was working on the molarity, because you are going to need to calculate out that molarity to do the graphs. So again, before you can do your second graph, you need to find the molarity. And the molarity right here is the molarity that we talked about earlier, the M1V1 equals M2V2. So any questions on how to find the molarity for these test tubes 1 through 5? Remember, test tube 5 is just the stock solution, so you only have to do a calculation for 1 through 4. But any questions on finding that molarity? All right, and the absorbance here, this is the sample data that I gave you. You're just going to fill it into this area. All right, so before we go on to the colors, let's go ahead and start talking about those graphs. Now, I know not everybody has access to a computer, so what I'm going to say is you guys are welcome to do this on your own, or you're welcome to partner up. So this is a lot of work to do, so if you want to partner up with somebody, you're welcome to do so. If you do not have a computer at home, then I definitely want you to partner up with someone who has a computer. So after lab, before you guys go, I'm going to see if anybody needs a partner, and if so, I will help you guys find partners. But if you feel comfortable finding your own partner, or if you want to choose to work on your own, that's fine as well. All right, so I'm going to start off with the very first graph. So this is based on part. All right, so right now I'm looking at part B data. So here is the wavelengths, and here's your absorbance. So I want to show you how to make a graph if you haven't before. Now, here I'm using Excel, and I happen to have a Mac, so it might look a little different if you have a PC. But you can also do this on a tablet, and you can also do it through Google Sheets. So Google Sheets allows you to do graphs just like this. So first of all, getting your data in. You always have to put the X value data in a column on the left and the Y value on the right, because Excel or any spreadsheet any spreadsheet program always assumes you have the X values before the Y values. Of course, there is a way to restructure, but I would say just go with their presets of X on the left, Y on the right. Then you're going to highlight these. And then depending on your computer, you may have the charts pop up right here. Because I am in projection mode, let's see if I can draw this out. So it looks like mine is not showing right away. Let's see, there we go. All right, so insert menu, and then right here I have these dots. This is what you want. You want a scatter plot. If for some reason you don't see it, you can go to the insert menu at the top, and then you can go down to chart. And again, you want to pick XY scatter. So whether you do it through here or through the picture of just the dots, you want to make sure you're getting the one that only has dots. You don't want dots and lines or the lines by themselves, just the dots. And it looks something like so to start off with. Now you have a bunch of white space on the left side of your screen. The way to get rid of that is to first click once here on the x-axis, and you'll notice there is a little box that surrounded it. So let me click off of there. All right, so first off, I click into the graph, and now I've got a box around the entire graph. Now I click so that there's a box around only the x-axis. Now I'm going to right-click. Those of you with a Mac, it's 2 fingers at the right. Those of you with a PC, you probably know how to right-click. And let's see, when I did that, I accidentally unhighlighted it. So let me click left and then click right. All right, so here you need to format your axis. It's going to default to starting the minimum at 0, but we don't need a minimum at 0 because we started at 430. So I'm going to change my minimum to 430. And that changes quite a lot here. So now we don't have all that white space. So that's just a good thing to do to get rid of the white space. Next up, what I need you to do is to title your chart. So you can click right in here, highlight, and I need you to do a nice descriptive title here. Tell me what I'm looking at. I also need you to title both your vertical and your horizontal axes. There's a couple ways to do that. So if you go to chart design, you have the add chart element, and you can go to primary horizontal. Oops, where'd it go? Try one more time. All right, sorry, axis title, primary horizontal. Oops, I accidentally removed the numbers down there. Try it one more time. Add chart element, axis title, primary horizontal, and there it goes. Add chart title, oops, sorry, axis title, primary vertical, and there we go. And now you can type into each of these. So here's where you would tell me on the x-axis you have wavelength in nanometers, and over here you would tell me that you have the absorbance, and there's no unit for absorbance, so it would just be absorbance. But I said there's two ways to do this. All right, so the other way is in quick layout, and both Mac and PC have quick layout. And so if I was scanning through here, I would look at this first one. It's got a title on the top and on both axes. So I would go ahead and click here. And it has a series 1. We don't need that. So I would just click and hit delete. Or on a PC, I believe you have maybe a backspace key instead of a delete to get rid of that. But that put both of them in together. So it's up to you. Either add chart element and then axis titles, or quick layout, and then I usually use this one because it's got a title on the top and on both axes. All right, so you're going to do something like so for your first graph. Again, make sure you title the graph so I know what I'm looking at, not just graph number 1. And you title the y-axis and the x-axis. So any questions on how to make that first graph? All right, and for those of you who are Excel and spreadsheet experts, I apologize for giving you an extra little lecture on how to use Excel. All right, so next up is your second graph. So here you're using the data where you took your test tubes and you measured them at 1 absorbance. That was your maximum, your wavelength of maximum absorbance. And these are your different test tubes. So I'm going to call this 1, 2, 3, 4, and 5. These are my test tubes. All right, so I did not calculate your molarity for you. These are the wrong molarities. I'm just doing this as a sample. So very importantly, do not graph your unknown. It will give you a really weird graph. So all you need to graph in here is the molarity and the absorbance. And you need to make sure they're in this order where the molarity is first because it's going on the x-axis and the absorbance is second because it's going on the y. And we're going to do the same thing. So you're going to insert here, or you can go to insert at the top. Make sure you're getting the XY scatter, and that should be only dots, no lines. And it should look something like this. So when you graph it, you're using very similar data to what I have here, so it should be a nice linear line going up. And you do need to title everything. So again, my recommendation would just be go to quick layout, grab that, and then delete the series. You don't need it. So I just highlighted it and hit my delete key. All right, so you're going to title this chart something descriptive. You're going to title your y-axis with absorbance. Your x-axis is molarity. I put here sample because it's not your molarity, so all you would need is molarity. All right, now there's something else you're going to need here, and that's a linear regression line. And so to get a trend line or a linear regression line, you're going to click on any point, and then you're going to right-click, and you're going to go to Add Trend Line. So now I've got a line that goes through here. From here, you need to format your trend line, and there's 2 things that I need you to choose. But first off, notice where I'm at. There are 3 options here, 1, 2, 3. You need to be in the 3rd option. So for the Mac, it automatically comes up. I believe for the PC, there's going to be a big plus sign over here that you will click on. But if neither of those come up, if you click over here, you should get the option of Format Trend Line, and that should work whether you're on a Mac or a PC. Scroll all the way to the bottom, and you need an equation, and you need an R-squared value. And now they pop up right here. I don't need this window anymore. I'm going to close it. From here, you can move this anywhere you want. I just need it somewhere where I can see it. So you can, make this bigger or smaller. Since I'm projecting, and I know some of you are on phones, I'm going to make this as big as I can here. You don't need to make it this big, but I just want to make sure everybody can see it. So you can move it around if you wanted to. You could change colors, whatever you want to do with it. But I need the equation and I need the r squared. So it does have to be done on a computer so that we can get the equation and the r squared. So the purpose of the r squared is it tells us about your data. Now, if this was in a lab situation, it would tell us how good of a job you did, both with getting your absorbances and also with your dilution. Sorry, I was reading a question at the same time. How will we turn in the charts? So here you can save it and then you can upload it as part of your lab. Yeah, I think it'd be too much of a hassle to print it out. So I would just say save it and then upload it as part of your lab. With any of the submissions, you can upload as many files as you want. All right. So here is a nice straight line. If you're not getting a straight line, if you're getting something funky, make sure you send me an email because since I'm giving you the data, I know the data is going to work out, but be careful not to put in your unknown. The way you're going to solve your unknown is with the line up here. So what we have here is the absorbance. So we have the y value. So I'm going to show you how we're going to use this right here. So your line is y equals, or I should say this line, not your line. This line is y equals 1.556x plus 0.001, like so. So that's the line, and this is your y value. So now I'm going to plug in 0.640 equals 1.556x plus 0.001. From here, I need to solve this equation, and when I solve the equation, I will find the molarity. So just for fun, let's go ahead and try that. So I'm going to take the 0.640 and I'm going to subtract out 0.001. And it tells me I get 0.639 equals 1.556x. So now I'm going to take my value and I'm going to divide by that 1.556. And it tells me if I round this that my x value, back up, it looks like it is 0.41, and then I'm going to round this to 1, so it is 0.411. That is the molarity that we're going to need. Oops. So in this lab, you're going to be asked for the molarity of your unknown, and this is how you find it. So you use the equation given here, and then you're going to solve out for x. So your unknown value right here becomes the y. And again, you're going to solve for x, and that is the molarity of your unknown. All right, can everybody see my iPad again? Yes, my cat made a guest appearance. Let's see. So I see a question from Tasso. Do you want us to plot that XY value? What do you mean by that? So Tasso, what do you mean by do you want us to plot the XY value? Oh, good. Okay, good question. So no, you never have to plot the unknown. Good question. Okay, and let's see. Can everyone see my iPad? Can anyone see my iPad? Yes. Okay, perfect. All right, so I know this is a long lab talk, so we're almost done. All right. So we've just talked about the two graphs, and again, if you don't have a computer at home, I want to make sure that you have a lab partner before you go. So if you're in that situation, make sure you hold on before you leave, and I will help you find a lab partner. The very last thing in this very fun lab is part D here. So part D is all about the colors. All right, so here we have a color wheel. And this color wheel tells us what nanometers or wavelengths are for certain colors. So for instance, violet is between 400 and 430 nanometers. Yellow is going to be between 560 nanometers and 490 nanometers. However, there's something very interesting that happens with the colors. So you may have heard that if you see, let's say, a red shirt, so it looks red to you, but it only looks red because it is absorbing green. Sorry. Try that one more time. It is absorbing green. So if someone has a red shirt or it looks red to you, it is because the light from the ceiling is giving out every color, but that shirt is absorbing the green, so the only thing left for you to see is red. So it's transmitting red, but it's absorbing green. So what this part is about is that normally we would have 5 different bottles out here. And I have some data for you so that you can know what colors we would have had out. The first question is this usable for what we call a Beer-Lambert plot, which is the graph that we just did. So in other words, the machine that we're looking at, the spectrophotometer, it's also called a UV vis, UV visible light. Is this something that we could use? Could we put this in our machine and get a reading? We can only get a reading off of colored substances. So if you have something that's colorless, it is not going to get a reading and it is not usable. Yellow, truthfully, we can use it, but very little. It's very hard to get readings off of yellow and light colors. What works wonderfully are things like blues, a dark violet, a dark red. Those work really well in these machines. So again, if it's colorless, you're not going to be able to get a reading. And when it says usable for this plot, it is only usable if it has a color to it. All right, next up, suggested wavelength for measuring absorbance. Here is an example. So here, if you saw orange in the bottle, then I would say yes, it is usable because there's a visible color. Where it would actually absorb, though, is in the blue. And let me show you where we find the blue. I'm going to use hot pink here. All right, so if I had orange, I go straight across. No, that didn't work well. All right, so if I had orange, I would go straight across and say it would absorb within the blue. So it would absorb between 430 to 480 nanometers. And so just choose any wavelength within that blue range, and that's fine for me. So again, if you see orange, it actually absorbs in the blue. It absorbs in what we call its complementary color. And the complementary color is the one directly across here. So just for fun, let's say that we had a bottle that was violet. What is violet's complementary color? Yes, I see yellow. So yellow is the complementary color for violet. So if we wanted to know at what wavelength would be a good wavelength to examine violet, what would a wavelength be? Give me an example. So I see 560 to 590, and I see 590 and 570. All of those work wonderfully. So if you had a violet bottle, you would choose a wavelength somewhere within here, and if you want to give me the whole range, you're welcome to. So I know that gets a little confusing, the idea of using the complementary color. But any questions on anything there? All right, so that's the experiment, but I want to briefly talk to you about the post-lab questions. But I know it's a long, kind of detailed experiment with lots of parts to it. So any questions on anything we've talked about so far? All right, So let's talk about the post-lab discussion questions. So first off, when you're preparing your stock solution, this was the very first solution you prepared, why can't we just subtract the volume of concentrated cobalt chloride from 50 milliliters and add that amount of water? So in other words, what they're asking is, why not just use your graduated cylinders? Why should we use that expensive volumetric flask? So any ideas on why we should use that flask? Why would anybody bother to use an expensive piece of equipment like that when you could just use a beaker, you could use a graduated cylinder? There we go. So I'm hearing from Andrew that it is more precise. That is exactly why we use it. So if we want, yes, and I see Tasso as well, if we want high precision, which we definitely do if we are going to put this in a spectrophotometer, we need that volumetric flask. So volumetric flasks, similar to burettes, can measure 2 digits after the decimal. Your beakers, those are kind of a guesstimate. If it says you have 50 milliliters, you kind of have somewhere between 30 and 60. And your graduated cylinders are a little better, but still not very much better. So again, we pay for that piece of equipment being very, very precise. So we want a very good reading. We need to use precise glassware. So any questions about that number one? All right, so number 2 says in step 5 of the procedures, we could have made each one from scratch rather than creating a stock solution. So basically what would have happened in class is you would have first made your stock solution. I know this may look like something else, but this is your vol flask. I'll even label it vol flask. And then from here you created 5 test tubes. And you use a graduated pipette to pull some of this, and I'll go ahead and put a beaker of water and some of the water into these test tubes. So the question is, why did you bother making this one at all? Why not just go straight from the solution that we had out and the water? Why did we bother to make this? What is the good and the bad about making that stock solution? So what we did is officially called a serial dilution. First we diluted it into the vol flask, and then we used our vol flask to do a second dilution. So why did we bother to do that? It does save time. Yes, it definitely saves time. And have a constant. So what do you mean by that, Andrew? So Andrew, I see you said have a constant. What do you mean by have a constant? Yes, so it's all coming from the same stock solution. So that is a constant for us. So first problem with, let's say instead of doing that, let me get another page here. You were to just take a beaker of our solution, and then you were going to take a beaker of water, and you were to make the test tubes out of these. Sorry, my test tubes aren't wonderful, and they're all mixture of sizes. So we've got a couple things going on. First of all, you would have to use a very small amount of the solution, and you would have to use such a small amount, it's going to be very hard to be precise. And the second thing is that you could essentially make a mistake for each one of these, and they'd be different mistakes. So when we do this kind of a experiment and we're trying to make a graph that looks like so, what we find is when we do it straight out of the original solution, we tend to get a lot worse data. When we make our stock solution first, we get a nice straight line. Now, sometimes that line is a little off of where it should be. And that could happen if whomever in your group made the solution might have made a mistake, but you still get a nice straight line because it's a consistent mistake through everything. So it cuts down on random errors, and those random errors can cause big problems with our data. It can cause that data to kind of go everywhere. So that is the advantage of doing it the way we did it, to not have these random errors, and similar to what Andrew said, that it creates sort of a constant. And in this question, they ask for a pro and a con. So it would save a little bit of time if you did it this way. So this would be a time-saving measure, but it tends to lead to more errors. All right, so questions on anything here for number 2 there? All right, so part B here, number 1, that is your first graph. So you've already done that if you've done that first graph. Number 2 says, why do we have to recalibrate at each different wavelength? So we're only calibrating with water. So why are we recalibrating? Any thoughts on why we have to recalibrate when we change the wavelength? Why do we calibrate at all? What's the point in calibration? So accuracy and for the equipment, but if you remember in the video, so he made sure that we had 0 transmittance when we got nothing in there and 100% transmittance when the water was in there. We want to make sure that the light is going completely through the water and the water is not interfering. So any amount of light that the water might absorb, we are essentially adjusting that out. So at a certain wavelength of light, some of that light might get stuck in the water, but we are telling it to take that out. It's very similar to hitting the 0 or tear button on our balances. So when you go to the balance, I always recommend you hit that 0 or tear button just in case it had said, hey, 0.2 before you got there. You don't want that in your weight. So here what we're doing is we're making sure that it's not picking up anything in the water. So it goes clear through the water, and that way the water, the aqueous component, is not going to cause any problems. It's not going to get stuck in that aqueous aspect of your solution. So any questions about that? We need to make sure that it transmits 100% through the water at every single wavelength. We want to make sure none of the light is getting stuck in the water. All right, and so number 3 I've already talked about a little bit. It says during the experiment you used the data to estimate the wavelength of maximum absorbance. Does the absorbance spectrum corroborate your estimate? Why or why not? So here what I want you to do is take a look at the data, and we made an estimation here. We said, well, hey, it looks like 510 is our wavelength of maximum absorbance, because that's where it is the highest. But then in your first graph, which looks something like so, we want you to take a look at the top of the peak here. Is it really at 510? So what we're asking you to do is compare the graph with this value right here and see if they agree, and just explain why or why not. So do they agree? Yes, the graph shows a peak right at this number, or you might say, no, my graph shows that the peak is really at about 515. So any questions on this experiment number 3? I'm sorry, not experiment number 3, question number 3. Sorry, I'm being distracted by hungry cats. All right. So we've already talked about graph number 2. So number 1 is just graph number 2. And we've talked about how to fill out this table. I don't know if I got a chance to talk about that R-squared value. So the R-squared value tells you how well your data fit the line. So our data fit the line pretty well, but if it was your experimental data, this is a way to check to see if you did a good job with your data. So if you get, say, 0.997, this is saying that there's a 99.7% chance that your data fit on this line. So that is showing that you did a very good job doing your measurements. If, on the other hand, you get, say, a 0.22, that's saying that to be a 22% chance that your data is going to fit on the line. That indicates that your data is kind of everywhere. So that's why whenever you do a trend line, I always recommend that you do an R-squared value, because that shows you how good your data is. Down here in number 2, this is where you are reporting the answer to your unknown, and we talked about how to solve for that. So any questions on anything from this page here? Can you get an R-squared value without a computer simulation? There are 2 ways. One is with a graphing calculator if you put in all the data points. The other is you can do a calculation, but it's a very long calculation. I am old enough to remember back in the day when we used to make students calculate it by hand, and trust me, you don't want to. It's ugly. But there's a lot of free programs online like the Google Sheets, and I'm sure there are trend line calculators online as well. But if you don't have a computer, you don't have access to Google Sheets, I want to make sure I pair you up with someone who does. All right, other questions so far? All right, and we talked about part D and about those colors. And just in case you're like, oh my God, those videos were awesome, I want to watch them again, the links are down here in the lab notes. But I know that was a long, long discussion about the lab, but any questions about anything from the lab?